Hello, welcome to another lecture on digital control systems technology. In today's lesson, we are going to be looking at some of the common components that we would be using when we are building digital control systems. So, when we talk about the various components that we would use in building digital control systems, some of the examples may be the type of systems that you may be building as part of the class projects for this course. Many of these components we may classify or we could categorize them into some broader categories. We can see some of them as electronic components, some of them as electrical components, some of them as electromechanical components, and some as purely mechanical components. And at this stage, given many of you have already started working on your projects and project designs, you may have already come across many of these components or many components that can come under any of these categories. And in today's lesson, we'll be looking at a number of categories of these components, things that we can categorize as sensors, transducers, actuators. So we will be looking at those things and some of the examples for such components. So, and again, this is more of a practical oriented topic, and you will be interacting with these components in your practicals rather in your project building activities, but we will look at some of the basic fundamentals about these components. The first type of devices that you would have when you are building digital control systems are the components that we can categorize as sensors. A sensor is basically a device that can receive and respond to a signal. So, the basic idea behind a sensor is that it can receive and respond to a signal. So, what we have in a sensor is it is something. There must be some signal must be produced from the environment, something like heat, something like light, motion, a chemical reaction. So, those are what we would identify as something that is happening from a form of energy that in turn would result in a signal. Then, sensors are devices that would detect these signals. So, the signals are produced by some type of energy, and then the sensor is the device that will detect that. And once such a sensor is detecting that signal, then it may convert it either to an analog or a digital representation of the said input energy or the input signal. The way that we would come across or we would use signals is that, for example, we could take a sensor such as a temperature sensor, for example. So, in the case of a temperature sensor, the property or the signal that we are going to start with is temperature, and that would be from or generated from the heat energy or the in the physical medium. So it could be in the room, in the air, or it could be the heat on a surface. So in any place, the physical medium, we would try to sense the temperature. So then what we would have is we would use something that is called a sensing element. So, sensing element is the basic component that is going to sense the signal. So, that is the main sensing part. Example here would be a resistance based sensor. So, that is a change in temperature would result in the change in resistance of the said sensing element. So, of the sensing element, if the temperature changes, the resistance would change. Then, when the resistance would change, that would result in what is called conditioning or some change being produced. So, in this case, it could be a voltage difference being observed. So, that is condition. So, then once an voltage difference is observed, then what we can do with that information is we can take that information and map it to a useful information. So, that is the useful information that we will produce. So, what we would have is, say the temperature changes, the resistance change. When the resistance changes, the voltage changes. Then the voltage changes, we can then again map to see what is the actual temperature change there. So, say here, say 0 to 3, so 3 volt change is happening there. So, the change is 3 there in terms of degree Celsius, let's assume. So, then that would result in a particular value of resistance change there. And that would result in a particular value of voltage change there. Now, then we need to have a mapping in between this 3 and this information. So, that is the last point that we will have. That is the signal that we would be ending up with. If we want to look at that from a mathematical point of view, as a mathematical equation, we could look at that as a sensor transfer function, something that we would identify as a sensor transfer function. So, in a sensor transfer function, there are a few main components that we could identify. It would be based on what we are trying to find is the output signal. And the output signal would be a function of the input stimulus. So, in the case of the temperature, the output signal would be based on the input stimulus, which is the temperature. So, in the case of say binary sensors, for example, this S could be either 0 or 1. So, depending on whatever the sensor, it could be 1. But another more sort of simpler scenario that we can see is if there is a linear relationship, a proportional relationship, then we can map that into a linear function. So, again, these are basic linear functions you would be familiar with from your mathematics courses. So, we can have a very simple transfer function. So, we would have a constant C, that is the stimulus value at, or rather output value at stimulus 0, and then we could have a constant times stimulus as the main transfer function. So, we could understand this a bit better using an example. So, let's take, for example, we have the output voltage of a thermocouple sensor. At 105 degrees Celsius, it is registering 42.3 volt. And at 0 degrees Celsius, it is registering 0 volt. So now the two questions, one is finding the transfer function, and the next one is finding the temperature when the output voltage is 15.4. So if we again go back to a simpler linear transfer function, we can try to map the information that we have into a transfer function such as this, and we can try to solve that to find these two answers. So the transfer function, we would start with S equals C plus ms. So if that is the basic transfer function, if you could start with the 0 volt case, where the constant C is 0 at stimulus 0, so that is the idea of C. So C is 0, C is that, so we can start with that, and then we substitute the values from the first case. So the second case would give us the C, so that is that, and then to calculate M, we would use this equation and we can calculate M, and then again substituting the values from the question here, we can calculate the temperature or the stimulus value there. So that is a very basic way of doing some calculations relevant to sensors and sensor transfer functions. In this case, this is a linear transfer function, but that doesn't mean all the sensor functions are going to be linear transfer functions. Some may be linear, some may be exponential functions, or there could be different functions depending on the type of sensor that you may be working with. If it is a linear transfer function, we would be able to solve it in this manner or do calculations in this manner. So when we think about sensors, the example that we were discussing so far is about a temperature sensor, a thermal sensor. Here, the physical phenomenon that we are concerned about is the temperature, is the heat energy that is we are concerned about. And there are a number of thermal sensors that we may come across. There are thermometers that can measure the actual temperature itself. There are thermocouple gauges. These are things that are made with two different or dissimilar metals, and based on that property, we can sense temperature differences or measure temperatures based on the differences on different metals. And then we can have things like calorimeters that again measure the heat reactions or heat outputs from chemical reactions. So there are various places where we may use such thermal sensors. So that is one type of common sensor that we may come across. Then there are other type of sensors such as mechanical sensors. So when we talk about mechanical sensors, we can have pressure sensors that can measure the pressure on a surface. We have barometers, and barometers can measure atmospheric pressure. So the difference is with pressure sensors, we are measuring pressure that is exerted on a surface, whereas in barometers, we are measuring pressure that is exerted on the atmosphere. Then we have altimeters where we can measure the altitude, the height above a fixed level, maybe from the sea level. We have liquid flow sensors, that is liquid flow sensors like water flow, measuring water flow. So if you are building something concerning water flow, any sort of liquid flow, and controlling pumps and things like that, you may use liquid flow sensors. Similarly, we can have gas flow sensors, which can measure gas essentially instead of liquid in a liquid flow sensor. And then one of the most common sensor that pretty much most of you would have around you is an accelerometer. And the example that where you may have it around you is in your smartphones or similar type devices that have an accelerometer that measures acceleration basically, and that can be used for various things. Movement and all sorts of things can be measured using such sensors. So again, these are what we would categorize as mechanical sensors. Then we have electrical sensors that can measure various properties of electricity, electric energy, things like ohm meter measuring resistance, voltmeter measuring voltages, galvanometers measuring currents, watt meters or watt hour meters measuring the overall electric usage or the energy consumption. So these are again different sensors that can be used for different measurements, and then in turn you can decide if you are controlling certain things. You can consider these as some factors in when you are controlling such things. Then chemical sensors, again, when you are building some control systems, particularly in industrial applications, chemical sensors can be very much of use depending on systems that you are building. For example, things like oxygen sensors can be used to measure the oxygen level in an environment or in either in the form of gas or liquid form. Carbon dioxide sensors, again detecting the level of carbon dioxide, or even things like, say, carbon monoxide CO sensors. Given carbon monoxide is a poisonous gas, detecting the presence of that in a environment that is being used by humans is the useful application. So again, you may have such things as well. Many of these chemical sensors may work with different things. They may use some form of IR sensors and measure the travel of infrared rays over different mediums, different things, and use that as a mechanism for measuring things. Then other than that, again, you will have light sensors or optical sensors, very commonly used. You will find things like photo detectors, photoresistors, infrared sensors, very commonly used. In many of you would be using some of these things in your projects as well. Acoustic or sound, so things like microphones or sesimeters or the acoustic wave sensors, motion sensors, Geiger counters. So there are a lot of different types of sensors. So the main thing to remember when you are talking about sensors is that it largely depends on what you want to do. So as we started identifying, sensors are going to be something that reacts to the change of energy in any form of in some particular form of energy. So depending on the system that you are building, depending on the application that you are intending to create, then you will choose a sensor that is capable of reacting to that energy, that is capable of addressing or reacting to the signal that is being produced from that energy form, and then convert that into a measurable form of signal that you can use in your systems and process further on. And the other thing to remember is many of these sensors may be either producing analog signals as voltage changes, or some may even produce the actual digital output of the information. Say, for example, there may be some temperature sensors. The output is some voltage changes, and then you will have to convert that into appropriate temperature values using some conversion algorithms, conversion equations in your program, in your control system program. Then other temperature sensors may actually produce the digital output itself. You will be able to receive the digital information, the temperature itself as a digital information that you can readily use in your systems, in your computations. So again, depending on the nature of application, depending on your requirements, you may be choosing any one of these sensors for your systems. The next category of devices that you may come across when you are building digital control systems is what we would identify as transducers. So the main property of transducers is that they convert energy from one form to another. They convert energy from one form to another. So we can look at that with some examples. If we take a microphone as an example, a microphone is a transducer that is going to convert sound energy into electrical energy. So it is converting from one form of energy to another form of energy. If we take something like a solar cell, for example, it is going to convert light energy into electrical energy. Then if we think about something like a thermocoupler, it is going to convert thermal energy into electrical energy. If we take, for example, a motor, for example, a motor is a transducer that is going to convert electrical energy into mechanical energy. So the idea behind a transducer is that these are devices that can convert energy from one form to another. So when we are building systems, this would be necessary in many ways. So either we may want to produce certain things in a particular energy form. Say, for example, we may want to produce movement. So then we may use a motor that is going to convert electrical to mechanical energy. We may want to capture sound. So the sound energy is going to be converted into electrical energy, so it can be captured in a system. Maybe we may want to do the inverse of that. So there, in a loudspeaker, for example, the electrical energy will be converted into sound. So these are the activities or aspects of transducers that we may come across in systems. So again, with transducers, we will have a number of categories, a number of type of transducers, again, based on the type of energy conversion that we have. So when we talk about chemical transducers, so these are ones that convert chemical energy into electrical energy, things like that. Batteries are a good example for that. Fuel cells are a good example for that. So these are conversions between electrical and chemical energy. Electromechanical transducers, here the two form of energies that are concerned are electrical energy and mechanical energy. So things like strain gauges, galvanometers, generators, they convert mechanical energy into electrical energy. Motors that convert electrical energy into mechanical energy. So these are in a way the inverse of one another. So those are electromechanical transducers. Then we have many other type of transducers such as electroacoustic. This is electricity and sound. Electromagnetic, electricity and magnetic. Electrostatic. So again, these are various different types of transducers. Depending on the need that we may have, we may use some of these in our systems. Then many other types such as photoelectric transducers. Again, these are light and electricity, thermoelectric, heat and electricity. So any sort of energy, one energy form to the other, if we can convert, then there could be a transducer that can do the conversion there. So again, as with sensors, the type of transducer that you may use in the system that you are building will largely depend on what you are trying to do and what is the input you have there, what is the output that you need to produce. Based on that, you will use a particular transducer there. Then we have another type of devices that are called actuators. So actuators are basically any device that can actuate or move something. So here what we are trying to do is any device that can actuate or move something. So the what an actuator does is it uses energy to provide motion. So it is providing motion. So given that it is an energy conversion, so it is using energy to produce motion, it is essentially a energy conversion. So given it is an energy conversion, what we would identify here is a actuator is a specific type of a transducer. Depending on the type of actuator, it would come under one of the categories of transducer. But the point is, the output here is the motion or the mechanical movement. Movement should be the output of this transducer. So not all transducers will be actuators, but rather all actuators will be transducers. Only the transducers that produce motion as an output will become a actuator. So if you, for example, think about the examples that we have discussed previously, you may be able to identify some of them as actuators. Say, for example, motor is something that is converting electrical energy into motion. So motor is a actuator. Whereas generator is using mechanical energy to produce electrical energy. The other output is electrical energy. So it is not an actuator. So you can think of those in that terms. So if we think about thermal actuators, a bimetallic strip, for example, is a simpler example of a thermal actuator. So this is where you have two metal strips of different thermal properties. So depending on the heat and their the change in heat, they may make contact or they may make movement and make contact. So you may find this in things, simpler things like electric kettles and things like that. So here it uses a thermal energy and converts it into a motion. So by that reason, we can identify that as a thermal actuator. So then motors are a good example of electric actuators. So DC motors, AC motors, stepper motors, all the different types of motors. Because at the end of the day, the outcome there is a motion, a movement is the outcome. And in addition to that, we may even identify solenoids as actuators, electric actuators. Then we may even have things like mechanical actuators. So something like a screw jack, for example, that you may find in a vehicle, it is taking mechanical input. Input is also mechanical energy, but it is converting that into a different mechanical energy. So what we are giving is a rotary mechanical input, or rotary motion is the input, and we are getting linear motion as the output. So again, it is a mechanical actuator because the output is a mechanical energy, but the input is also mechanical. Then some of the common other types of actuators that you may find is hydraulic actuators, where a hydraulic fluid is pumped into something to make a movement. So you may find these in hydraulic jacks and things like that. A similar concept that is using compressed air is, again, air is a fluid, but in this case these are identified as pneumatic actuators. So again, here what we have is air in these chambers, and based on the air there will be a movement here. So again, those are that we would identify as other pneumatic actuators. So again, hydraulic actuators and pneumatic actuators, we would particularly use them in building systems, particularly when we need linear motion, because most of the motors may be used to produce rotational movements, and these type of hydraulic actuators, pneumatic actuators, we may use them to producing linear motion. Now, let's sort of briefly touch upon motors specifically, a type of actuators. The reason being, motors are some of the common type of components that you may be using in many control system applications, many systems that you may be building and designing and building. So just as an introduction, let's look at some of the differences between servo motors and stepper motors. So the idea behind the main difference between stepper motors and servo motors is the first idea to remember in terms of motors is motors have these magnets and a number of pairs of magnets normally, and so each pair we would be able to identify as poles. So when they are at a particular pole, a particular phase will be excited. Also, when a particular phase is excited, that is the pole that is going to be magnetized. That is where the motor is going to wind towards to. So the main difference between stepper motors and servo motors is, in stepper motors they will have nearly, say, 50 to 100 poles in a brushless stepper motor, whereas in a servo motor they may only have 4 to 12 poles. So the main sort of advantage of having more number of poles in a stepper motor is that we would be able to very specifically make movements in a stepper motor, whereas in a servo motor we would not be able to very specifically make smaller or smaller movements like that. So because stepper motors have these large number of poles, we can slowly move between their poles and we can make a lot of accurate step moves, hence the name stepper motors. Whereas with servo motors, because they have fewer poles, we will not be able to move them as accurately as that. So then if we want to make accurate movements with servo motors, we need to have additional sensors to detect their movement, say for example like an optical encoder or something, we may need to use some additional sensors, and then those sensors can be used in a feedback loop, and then that can control the servo motor. Whereas in the stepper motor, we can directly give the input to make smaller movements and make accurate movements. So, in the context of open loop and closed loop systems, stepper motors would normally function in a open loop fashion, but with every increment of pulses they will make a move, whereas servo motors will function in a closed loop fashion, and they will have to adjust their position based on the feedback that is gained from the output. Then another thing that you may find when you are using these different types of motors is that they have different load handling capacities and particularly torque to speed curve. So that is, some of them can produce higher torque at lower speeds, and that property will change differently. So if we keep on, say, increasing the load, when we keep on increasing the load like this, the difference, say for example, a DC servo motor has a very linear uh, change to that, whereas an AC servo motor has a slightly different change, a more, so it will dip, and then so it will, there is a different point where it will meet the load. So depending on these characteristics, we may be able to choose between different motors for our particular applications. So depending on the uh, place where they meet the operating point, the load meets the curve of the particular motor, we may be able to handle more loads in a particular type of motor than the other. So again, this is largely depending on the nature of the motors and things like that. Now let's also look at an example of how do we go about controlling stepper motors. Because given stepper motors are very accurately controllable, there's a good chance we may use stepper motors in many different applications. So we look at some of the common approaches that we may take in controlling these stepper motors. So one of the main properties that we would have with a stepper motor is what is called a step angle. So that is how many steps that we have. Say, if a stepper motor has n number of steps, then the step angle is 360 divided by that number of steps. So, how many degrees it will rotate per step. So, that is the step angle. So, then one of the things that we would, couple of things that we can calculate is angular velocity and the speed of rotation. So then again, uh, uh, we can, these are again things you may be familiar from your mathematics. We can calculate angular velocity. So, say if the pulse frequency is given by fp, so then the frequency, and then we divide that by the number of steps that we would take, we can get the angular velocity. So 2 pi and divided by number of steps. Then rotation is again the pulse frequency, we multiply that and then again divide that by the number of steps. We'll look at that with some examples now. So say if we have a stepper motor that has a step angle of 3.6, let's calculate some of these things. How many pulses are required for the motor to rotate through 10 complete revolutions? So we want to get 10 complete revolutions, and what pulse frequency is required for us to uh, uh, rotate at speed 100 revolutions per minute. So we want to rotate 10 times, and then we want to achieve 100 revolutions per minute. So we know the step angle is 3.6. So if you want to calculate the number of steps, just put that in the equation, and we will be ending up with 100 steps. So the motor has 100 steps. So now if you want to do 10 revolutions, so so we will again replace these 10 revolutions, so that is 3600. So they are the if we divide that by angle, so we need 1000. So then we need 1000 pulses, because like per rotation it is 100 step angles. For 10 rotations we need 1000 pulses. Then for the angular speed, again we want to achieve 100 revolutions per minute. So 100 into 60 fp is what we need to calculate the frequency, and so then we can calculate that as 167 hertz. So this is just an example of how to work out a stepper motor. If you are particularly trying to control a stepper motor, this is how you will do the calculations inside your application when you are programming your application. So again, this is something that you may do if your project that you are building concerns a stepper motor. So, in summary, what we have covered today is mainly three things. One is sensors. Sensors are devices that receive and respond to signals. Transducer is a device that converts one form of energy into another. And actuators are devices that convert energy into motion. Then when it comes to sensors, there are many different sensors as long as they are able to measure some phenomenon of energy or some form of energy change in that and detect that and respond as a signal. Then transducers, again, there are many types that we may come across in our use depending on the energy conversion that they do. And a particular factor about actuators is that actuators are a subtype of transducers where the conversion of energy results in motion. So the point is, all actuators are transducers, but not all transducers are actuators. Some transducers will convert into other forms of energy, and the ones that convert into motion energy, we will categorize them as actuators. Then finally, a point about your projects. Currently, you have already submitted the project design documents, and at this stage, given the situation with lockdowns and everything, we are not very sure about when it may be feasible, if it may be feasible for us to have physical lessons and opportunities for you to work on building the projects. And given the nature of these projects, It may not be practical to build them as it is without having a physical environment, physical presence. But what we may go about doing is, I may suggest you implement your project designs in a simulation software, and then we can do that as your final project building if we are not able to do the actual project building. So then that would be considered for your main project assessment as well. Then you can also do a presentation for that. So that would be the overall project part of this course. So those details I will share in the coming days and weeks. And depending on how the semester progresses, we can make a decision as to how to go about this. So if you have any questions or concerns regarding how to go about this particular aspect of the course, particularly the projects and the future of the project building, please let me know, and we can have a discussion about that on LMS and then proceed with that. So that's all for today's lesson, and thank you for joining in. See you next time. Bye.